The following content is for entertainment and educational purposes only. It does not constitute means for diagnosis, healthcare advice, nor treatment. Make use of a qualified healthcare professional for such purposes.
Good morning, everyone. My name is Dr. Charlene Ortiz, and today we're going to begin with a new section of our class material. Today, we're going to talk about sensation and perception. Why is this relevant to the field of psychology? Well, previously, we talked about the biological basis of behavior, because as we know, anything psychological, mental illness, behavior, emotions, thoughts, anything you can think of will always have a biological foundation. But how exactly do we come to understand our world? Well, we do so through sensation and perception. I like to think about sensation and perception as the way that we come into contact with new stimuli and how we process said stimuli. And this is immensely important because if I know what the norm looks like, right? So for example, I know that normally when we have a stimuli of light, we see certain things, I can predict what the next stimuli might be. So for example, if I see a room full of people, chances are I will see a room full of people again. But if I have some sort of abnormality, I should say, for example, I will start this sensation of this perception as I'm hallucinating, right? So there's something else going on. So I like to think about sensation and perception in that factor. So let's get started. Now, we have many different means of stimuli, right? We have different means of stimuli. One of the first ones that we're going to talk about today is the stimulus of light, right? Our first stimuli is the stimulus of light. Now, as you may know from other courses, or maybe some introductory courses, or some advanced courses in high school, or maybe some courses today, you will know that light as a stimulus is an electromagnetic ray, right? It's electromagnetic radiation. Right? And it travels in the form of a wave. Now, there are several characteristics that I would like to talk about when it comes to the stimulus of light. And also later on, when we talked about the stimulus of sound, they're very similar in that regard, and that is their behavior, right? So for instance, light is a wave, right? And therefore behaves like a wave, which means that we have two characteristics. The first one is amplitude, right? And if you move towards the right of your screen, you'll notice that amplitude, right? This is the wave, right? This is the light wave. You can also think about this illustration here. You can also look at it as if it were a sound wave because they behave similarly. So what is amplitude? Amplitude is the height, right? Height of that wave, right? So when you're thinking about amplitude, right? For those of you who play musical instruments, you know that amplitude, right? Think about an amplifier, right? It amplifies, right? It sounds bigger, right? So that's a good way to remember what amplitude is, right? That height of that wave. And another interesting characteristic of light, as well as in sound, is the wavelength. Wavelength. So let's look back again in our little illustration here to your right. So we talked about amplitude as the height, and notice that this wavelength has different peaks, right? So there's one peak here, another peak here, another peak here. So wavelength represents the distance, right? The distance between those two high peaks and these two right here. That's what we will refer to as the wavelength. Now, something interesting about the light as a stimulus is that you need to remember that there's only so much of light that humans can see. We're only limited to a certain range of that stimuli. And if you look back in our screen to the bottom right, you notice that light as a source, there's a wide range, right? So there's a wide range of stimuli that exist. However, humans are only able to capture just a slim portion of that wavelength. Now, it can vary in purity. And when we're talking about purity of that stimulus, I want you to think about instances of what can influence my perception. For instance, the saturation of that image, of that stimuli that we're receiving, and also the richness, right, of those colors. And what do I mean by saturation? What I mean by that is basically the amount of whiteness in a color. Any questions about that? Deal. Now, when we are thinking about light, right? Remember that something that I like to say is we don't see with our eyes, we see with our brain. And that is because the stimuli that you are receiving right now, for example, looking at my shirt and seeing, okay, so Dr. Shar is wearing a blue shirt, the room is relatively well lit, right? That stimuli that you are receiving right now wouldn't be as important as if it cannot be interpreted, right? If I cannot interpret the stimuli, then it will become useless, right? But in order to do so, we convert this stimuli, right? This type of wavelength, and we're going to convert it into neural impulses. So if you remember in the very beginning, when we started talking about biological foundations of behavior, I mentioned that in regards to our stimuli, right, neurons, right, carry down that information, right, through electricity, through electrical, chemical communication, and that will be transported to be interpreted. And if you recall from our previous chapters, you'll remember that that information would be processed by your occipital lobe, right, which is in charge of visual stimuli. But how does that happen? How do we conduct this sensation? So here, the process goes like such, I should say. The first thing that's going to happen, we are going to receive that stimuli, right? We're going to receive that light. And the first thing that's going to happen is we're going to have our little windows in our eyes, right? We're going to have these little windows in our eyes. Now notice that the first thing that's going to happen is that that information is going to pass down through the cornea. Going to pass through the cornea. And the cornea, I want you to think about the cornea as a transparent window, right? That's what the cornea is. It's a transparent window. Now, once that stimuli keeps going, it's going to hit the next aspect, which is the lens, right? It's going to go through the lens. And what happens with the lens is that it's going to adjust its curvature in order to focus on images. So for instance, for those of you who are a little older, right? You remember old-timey cameras where you can actually physically see the lens changing its shape in order to be able to focus on that image, right? To provide a little bit more clarity of that image. Going back to our illustration, you will see that when we're thinking about the lens is going to reflect, right? It's going to reflect that image later on. It's going to reflect that image to the back of the eye. Now, interestingly, we have the pupil. And the pupil, which is this area here, is going to regulate the amount of light. How much light am I going to allow to go through this chamber here? How much light am I allowing to pass through that chamber? Now, afterwards, something important that needs to occur is that generally our images, right? So for example, this is the image, this is the stimuli that I'm looking into. Generally, that image is going to be reflected upside down. That image is reflected upside down. What's going to occur is that during our processing, right? During the processing of this information, this image will be then reverted. Image will be then reverted. Now, any questions so far about how that stimuli came to be transported or moved towards the inside of this chamber? Good so far? Yes. I'm sorry?
Because you said it's reflected inside down.
Right. The image will be reflected upside down.
Does it go back?
So it goes back. So think about when we're switching that perception, it's going to go back during the interpretation, right? So when you actually start processing the image, because remember, you can't see with your eye. So there's no processing here. This is simply a receptor. The eye is a receptor. The skin is a receptor. Your ears are receptors. There's no processing there. So that image is going to change during processing in your brain. All right. Does that answer your question?
Yes.
Okay. Good deal. So something else that I need to mention is that we're going to have specialized areas, right? We're going to have specialized areas. Before we cover more of the specialized areas, let's talk about individuals or issues that we may have when we have issues with processing, or I should say, gathering that stimuli. So what happens? One of the first problems that we may see is being nearsighted. What does that mean? It means that the focus of that light from objects that are far away, it just so happens to fall a little short to the retina. What does that mean? Well, if we go back to our illustration, you'll see this area here, right? So if you guys can see this very thin line, this blue line, I'm going to follow along here. This is the retina, right? This little thin line here. When we're thinking about retina, I want you to think about that inner layer of your eye. So with persons who have that problem, what happens is that this focus, the focus that you're having about in this image, is not reflected directly, right? It just falls short, right? So it can't reach that layer, right? So for example, an image that was reflected accordingly does hit the retina, right? It does hit the retina. Whereas for someone who has this disorder, the image just falls short. Just does not reach the inside, right? It doesn't focus. Now, with persons who have the opposite problem, right? People who are farsighted, that focus from close objects goes beyond that, right? It goes behind the retina. So what does that mean? Well, for individuals who are farsighted, contrary to our nearsighted individuals, instead of falling short, this image goes beyond. it tries to reflect the image behind this layer, behind the retina. So it attempts to go beyond. So it will sit behind that layer, right? Behind the layer of the retina. Any questions about that? All right, so let's talk about the pupil. Now, as we noted, similar to the lens that attempts to focus the light, when we're thinking about the pupil, its responsibility is to regulate the amount of light that is going to pass later to the back of this chamber, right? So it's attempting to focus that light, right? It's attempting to regulate that amount. So the lens will try to focus, and the pupil will try to regulate how much of that light will be received, and the lens will try to focus. So a good way to remember that is lens is focus and pupil is amount, right? That's a really good way to remember. Any questions about that? Now, in regards to the retina, so let's start talking about a little bit more of that specialization, right? So now we're going to move towards, let's start moving away from the eye. Let's talk about how we're going to process this image that I am encountering, right? Because remember, your eye is a receptor, right? Your eye is a receptor. I like to think about receptors and sensation, because people confuse sensation and perception, right? So sensation and perception, sensation is how we are receiving, right, that information, and perception is our interpretation of, right? So sensation, right? Good way to remember that is that sensation is what we sense, and perception is what we perceive, right? So think about the microphones that are in this classroom. The microphones become that sensation, right? But your perception is whether or not you think I have a beautiful cherub-like voice, right? That would be your perception, right? So that's a good difference. Now let's start moving towards that angle. So as you know, the retina is that neural tissue. Now we're starting to use the term neural, right? So for neurons, right? Neuron. There we go. And remember that neurons are that specialized cell that carries information and starts moving it towards the interpretation of the brain. Now we start seeing the term process. And we're going to start sending that information to the brain for interpretation. But how does that happen, right? We have different types of receptors, right? I'll start with the fovea first. The fovea, if you remember from our retina, which is that inner lining, right, of your eye, the fovea is a very small spot in the center of your retina. And if we go back to our illustration, if I clear this image here, the fovea is this area right here. Let's do something else. Let's find a better image for you guys for the fovea, because I don't think this image does it justice. Right. Or find one that's a little better. Here we go. Let's work up a little better. Perfect. Share our screen. Here we go. So notice that this is the back of your eye, right? Where your or your retina is, right, that inner layer, right? And notice that the fovea is a very tiny dip, if you will. It's a very tiny dip, it's a very tiny section. And if we were to zoom in, you'll notice that we will have that tiny little focus point, right? So for people who are nearsighted or farsighted, they're just simply unable, whether because they fall short or they go behind the retina. So they are unable to carry and focus that information here. Right, so this is what the fovea looks like, right? It's that inner layer with the retina. And then we're moving a little bit more specifically to the fovea, which is that tiny focus point, that tiny spot, if you will. So any questions about the fovea?
So with nearsightedness and farsightedness, when you're saying that the light falls short or goes past, are you talking about the image itself? Like light is hitting the back of the eye.
Right, so when it falls short.
Where the lens is trying to focus.
Right, right. Good deal. So let's continue with that specialization. Now, we talked about the fovea, but we need to talk a little bit more about which cells, right? Which cells are responsible for different types of processing. And no, thought I was gonna say, okay. Let's talk about cones. Let's talk about cones. Cones are specialized visual receptors. And if you notice, cones start with a C, right? And what else starts with C? Color. Therefore, cones are specialized in receiving that information that deals with color, right? So they're specialized in color. But we also have another cell, right? Called rods. Right? Now, when it comes to rods, we like to think of them as that are almost a little bit more dark, right? When we start losing, right? We start losing that light and we start to look into, okay, the color vision when it's dark, right? We're starting to think about that darkness. So I'm not quite sure why this information says that, but the correct thing to remember is that rods specialize in night. We're talking about darkness. All right, so it's a little reminder, remember that rods are night and cones reflect upon color. Any questions about that?
Carrots actually help with night vision.
Sorry?
Do carrots actually help with seeing at night?
It's funny you say that. A lot of people, I've heard a lot of people say, oh, being carrots are going to have better vision. My understanding, that was part of a campaign to have people eat more carrots. Yes, sir. Yeah. Yeah, I remember it being some sort of, not remember, of course, I wasn't around. But I do remember it was some sort of, campaign to have people eat more. So, interestingly, we do have the ability, actually, humans have a pretty good capacity of adapting to seeing light in darkness, right? It's not that close, but it's pretty close to being able to identify just one photon. So it's actually pretty good. We actually, once we start adapting, for example, if this room were completely dark, it will take us a minute, but then we can start identifying just a little bit of light. So that is because we become more sensitive, right? We become more sensitive. Now, information processing in our retina, however, now we're thinking about that receptive field, right? So if you remember, that receptive field in our retina is stimulated by firing that cell, right? So remember that cones are in color and rods allow us to do vision when there's nighttime, when there's darkness. Now let's be a little bit more specific. Let's be a little bit more specific. Now that that information has been received, now that that information has been received, and we have that sensation, right, in our eyes, now it's time to actually process this information. How does it leave, right? How does it leave the receptor in order to start being processed by our brain? Well, we're going to do so through our axons, right? If you remember correctly, when we have a neuron, that long elongated part of the neuron, right, is the axon. So you'll see that you have axons that will start leaving the eye. We also refer to them as optic nerves. Right? So these little structures right here, optic nerves. Now, what happens afterwards? Well, what happens is we're going to come across this structure. This structure is known as the optic chiasm. Optic chiasm. And what occurs here is that the axons from each side, right? So remember that any stimuli that comes from the left side is then processed through the right side, and the information that goes from the right side will be processed through the left side. So what's going to happen in the optic chiasm is that we're going to cross over, right? We're going to cross over those hemispheres. Is going to project on the opposite half, right? So left to right, right to left. And you're thinking, well, what's the point? Why can't we just go from left to left and right to right? Well, it's so that we have the ability, right? It's to ensure that those signals do in fact go through both hemispheres. Right, that we're not losing any type of information, right? Everybody gets a piece, right? Everybody gets a piece. Now, when we are thinking about that processing, right? When we are thinking about that processing, now we're starting to look more into the visual cortex. Right, we're moving into the visual cortex. Now, what's going to occur when that information is passed through, that visual input that you have received, that stimuli, it's now going to meet and it's going to move toward the occipital lobe in order to be interpreted, right? Because so far, that image that you just saw has not been interpreted as such, right? So if you saw a flower, all the way, all this process that I have been trying to take us on a trip on, this has only been the process of sensation, because once it hits the brain, now we can start interpreting, right? Now we can start interpreting what this image is. Now inside the visual cortex, in our occipital lobe, we're going to have feature detectors. Feature detectors. What are those, right? What are those? What are those? These are going to be neurons that are only going to respond specifically to a very specific feature of more complex stimuli. So what does that mean in the Queen's English, right? What does that mean basically? So think about if I were to give you guys a task, right? So for example, we need to work on a yard, right? So we have to weed eat, we have to leaf blow, we have to pick up the trash. So notice that one of you is going to have the task, okay, Petey is going to leaf blow and Yolanda is going to raid. Similar to that is that very specificity of those receptors, because one is going to look at that image and say, this is the characteristic of curvature, and this is the characteristic of so on and so forth, just like you would divide specific tasks, and all together, they would say, okay, it's curvy, and it's red, and it has a stem. Then once we start putting all these characteristics together, you would say, oh, it's a flower. But notice that they're only going to respond to that specific stimuli, right? If the stimuli is not present, they're not going to react. Any questions about that? Let's talk about viewing the world in color. How is it that we understand the world? Now, the most diverse variations, right? They're going to come not so much from the curvature, or if something looks far away, if something looks it being nearby. The most diverse aspect of viewing is going to be because of our mixture of colors. There are two theories, right? There are two theories that attempt to explain why is it that we are able to see things in color. The first one, we're going to talk about abstractive first. The first theory will state that we're going to remove some of the wavelengths, right? Therefore, we're going to have less light that was originally there. So for example, if we go back to our earlier illustration, right, when it comes to color, right, this is a really large representation of this smaller representation. So that theory would say, well, if I subtract blue from purple, I'm going to be left out with red, therefore the image is red, right? That's what that theory proposes. On the other hand, we have the additive color mixing. So now this one's proposing, we're not going to take away, we're going to add, we're going to superimpose these lights, we're going to superimpose these images in order to come up with more mixture that was already there. So in this illustration here, you have towards your right, notice that here I will be adding a layer upon the other, right? We'll superimpose these layers of light. Whereas in our next method, we're going to try and subtract a wavelength, right? Trying to subtract a wavelength. Any questions about that? Yes, sir.
So there are two theories that attempt to explain which implies to be mutually exclusive.
Go ahead.
So the way you word it sounded like you're implying basically that they're mutually exclusive, both types of color. Is that the case, or
It's not. That's a really good question. So if they, our friend here is mentioning Daniel. Did I remember that? No, that's not your name. I thought it was Daniel.
No, it's there.
Oh, I got it right. You should feel special because I never remember anyone's name. So Dr. Daniel over here is saying they sound mutually exclusive, and they're not. They're not mutually exclusive. We have tested these hypotheses, and it turns out we use both methods, right? We either superimpose these images or we attempt to subtract. Now, we also have the idea of the Trichromatic Theory. Trichromatic Theory. And as it stands, notice that it says tree, right? Which sounds an awful lot like the number. That's exactly what it means. It notices and it stands that there are 3 types of receptors that have the ability to differentiate, I should say, to have some sort of sensitivity to different wavelengths. We have these 3 types of receptors. And ideally, the Trichromatic Theory proposes that we have wavelength receptors associated with red, green, and blue. Red, green, and blue. This theory argues that we are able to see any colors because of adding those 3 colors. So red, green, and blue. Now, let's talk about color blindness. Anybody here colorblind that they know of? Right, good deal. How's that going?
It's okay. I really have trouble with it.
That's interesting. Not a problem. For some people, that could be an emergency. Having, they start going to town and throwing away their controller, right? Generally, color blindness is more prevalent in males than females. Can anybody tell me what? Females can't. Go ahead.
It's an X disorder.
I'm sorry?
It's an X chromosome.
It's an X chromosome disorder. And what else? It's a really good question. Anybody else know why? Yes.
Typically, females have more cones than males.
I'm sorry?
Don't females typically have more cones than males do?
You're correct. Females can distinguish color much better. That's why sometimes if you're like decorating a room or something with a girlfriend, and you're like, this is burgundy moonlight color, and you're like, that's just red. I don't know what you're talking about. But then your girlfriend or your spouse or your sister, your mom goes a little bit more specific. Well, that's because females can actually detect color better. Not going to get into details so much about why that is, but the theory is that, back in the day, females tend to be more of the gatherers, so they could distinguish between different types of herbs and fruit, and because of that, they started developing, okay, this slightly different colored one, this one's going to kill the whole tribe, right? So let me grab this one. So they started developing a little bit better color vision. By the same token, males tend to have better spatial recognition, which matches the ability to hunt and gather, right? So in their case, they needed to be able to hunt. Therefore, their spatial ability was more necessary than color, whereas with females, color probably was the better option for survival. We talked about adaptation in our last lecture, and in the last lecture that I recorded independently, I go very much in detail upon that. Now, something really interesting, right? Something really interesting. Your book doesn't mention that, but I like to throw in that little detail is that females tend to be more receptive of color. So we're thinking about these color theories and you're thinking, what does that have to do with psychology, right? What does that have to do with psychology? Well, I'm going to give you a real life example. think about if you're witnessing a crime, right? Walking down the street, you're walking your dog, and then all of a sudden you see a vehicle speeding away. You know, there's a guy on the floor, right? You're thinking, wow, this guy just got, robbed or something like that, just got assaulted. You're thinking, well, what does that matter? Well, think about witness testimony, right? Think about witness testimony. One of the first things that you're going to be interviewed about is what was he wearing, right? You say, well, he was wearing a blue shirt. And then your girlfriend that was with you, she's like, I think it was like a gray shirt, right? So notice that our sensation can impact our perception. And that could even be something as important as witnessing a crime, right? So notice that there are instances, right? And we are particularly interested in aspects of that nature, right? Our perception of events. For instance, we tend to favor bright colors instead of dark colors, right? So how can that influence your behavior? Things of that nature. We talked about the Trichromatic Theory. Let's talk about the opponent process theory for color. So previously, we talked about the trichromatic, which states we have 3 types of receptors, whereas the opponent process, it depends on which receptors basically are antagonistic to those 3 pairs of colors. What does that mean in plain old English? Well, that means that the colors are complementary, right? This theory proposes that colors will be complementary in the sense that one is going to shut down the other, right? So think about this. Say I have a red receptor, and whenever the red receptor is on, it's going to shut down my blue receptor, and vice versa. My blue receptor is on, that means my red receptor is on, right? So one is antagonistic. One stops the other from becoming activated. So what happens is, according to the opponent process theory, is that within that first stage, the cones seem to behave in this fashion, right? So we're going to activate either a red, a green, red, green, or blue. The first step, it appears that it does serve the trichromatic theory. However, later, when we start processing the image a little bit more in detail, then we start this antagonistic process. Then we start shutting down, okay, it was blue, so let me turn off and inhibit that red receptor, for example. And I remember this was like a whole thing a couple years ago, seeing which one was the correct one. And usually I don't show the discussion activities, but this is a really good example as to how light, right? How the processing affects our image. So some people would see a white dress, and some people would see a really dark dress. By the way, this is the correct one. All right, so they would see this or this, and then we have the corrected. Any questions about the perceptions? And again, both the opponent process and the trichromatic don't cancel one another, right? They're complementary. We actually use both methods in order to understand color, okay? So they don't cancel one another. Now, we were talking about, first of all, how is it that we perceive light? We talked about how exactly that processing for color is. Let's talk about how is it that we perceive forms and patterns, right? We talked about color. Let's talk about patterns, right? Let's talk about patterns. Now, it's interesting because the same visual input, right? For example, if you're seeing an old person, if you're seeing a young person, and you say, for instance, oh, I thought, when you're doing this witness testimony, you're saying, oh, I thought he was like a really young guy. And another person that was a witness says, no, I thought that guy was in his like mid-50s. The same stimuli can result in so many different perceptions. Now, there's multiple aspects that affect us in regards to detecting patterns, forms, and having an accurate perception. Now, we like to use reversible figures. That is that one image, right? One drawing is compatible to two different interpretations. And this would be a relatively good example of such. So if we look at this image here, how many of you see a duck? About a third, half of the class. How many of you see a rabbit? Right? Who doesn't see the rabbit? You're like, what? Where is that rabbit? How many of you don't see the duck? It's like, you guys are crazy. All right, so if you perceive the image this way, you would see the beak, right, in the back of the head of the duck. Whereas, if you look this way, see, these are the ears of the rabbit. This is the eye of the rabbit. This is the little nose of the rabbit. Like, what? Where did that come from? Right? So notice that the same image can lead to different types of perception. Now, in perceptual set, what do I mean by perceptual set? It's basically you are ready to receive a very specific stimulus, right, in a very specific way. What does that mean? That sounds pretty cryptic, right? But I'll give you an example, right? Let's think about the example that I just gave you. You're walking your dog in the park, and then all of a sudden you see this man coming into the car, fleeing away, and then you see a guy in the dress like, whoa, this guy just got robbed, right? And in this example, right, if I were to show you a video, right, CCTV footage or ADT or something like that, you start watching this video, you will say, yeah, that's the guy. That's the guy right there. That's the man that did it. How do you know it was a man? Because I said it was a man. That is having a perceptual sense. Right? You are inclined into perceiving something that I told you about. That is actually really interesting for those of you who do forensic psychology. And individuals like me, whose my specialty is forensic psychology. Whenever we are conducting an interview with a person that has been assaulted, right, in any fashion, right, sexually, physically. Imagine if I start that conversation and say, what happened during the assault? That sounds like a really basic question, right? A lot of you would say, yeah, that's exactly what you should ask. I'm telling this person they were assaulted. What happened during the assault? For all we know, this person doesn't even perceive it as an assault. For all they know, oh, I just had a fight with my girlfriend. I wasn't assaulted. Notice that I gave them that perceptual set. Right? So she only beat me up, for example. But now I use the term assault. Now I'm going to put that idea in that person's head, and maybe during testimony, that person would say, well, I was assaulted by my girlfriend. Right? Now, another aspect about how we tend to perceive different things, even though they're the same stimuli, is by inattentional blindness. And in this case, we fail to see visual objects. We fail to see a display because of your attention. You were simply focused on something else. So let's think about another case. Back in 2008 or 9, I was robbed at one point. It was a very scary experience. Nothing happened. You know, they only took my wallet, nothing happened. Back then, I thought it was because of my car. I just bought that car, and I thought, oh man, they're gonna take my car. If I were to tell you what they look like, I can't tell you what they look like because of inattentional blindness. Why is that? I can tell you exactly what kind of gun they had. My attention was immensely focused on that factor that is life-threatening, right? My attention is focused like, this looks like a real gun, this looks like a real pistol, right? So I can tell you if it was black, if it was brown, if it was chrome, right? If it was a revolver, if it was a pistol, because I have inattentional blindness. I am focused on one event of something that's really specific, right? And notice that's not on purpose. And a lot of people would tell you, oh, this guy followed me with a machete. They can tell you exactly what a machete looked like. Problem is there's 10 million that look just like, right? So it's not pretty useful for eyewitness testimony. So in keeping with that type of perception, I'm going to show you an illustration of such. Okay. All right. I'm going to show you an example of that type of perception issue. All right. Let's put it up on the screen. This is actually a very popular test. Some of you might have seen it, and if you've already seen it, just keep it to yourself, because there's a lot of people here that might have not. So let's look at this example. This is an example of perception difficulty.
This is a test of selective attention. Count how many times the players wearing white pass the basketball. How many passes did you count? The correct answer is 15 passes. But did you see the gorilla? This video is from research by Daniel Simons and Christopher Chabris.
So notice that some of you might have not even realized there was a grown person walking down the middle, right, wearing a gorilla suit. Because some of you were focused solely on that instruction, right? You were solely focused on that specific stimuli. Whereas some of you were trying to look into, okay, this must be something to it, right? But you were led into counting how many passes there were Whereas for some individuals, they didn't follow the leading question, right? That could be an example of having a perceptual set. Any questions about that? Any questions? Good deal. Notice, like in the example that I just gave you, like for example, talking to an individual, talking to a witness, saying, what did the man do? Well, how do we know it was a man? We would say something like, what did this person, or what happened would be a much better question. What happened that Friday? That would have been a way better question. Because it's not leading in any direction. Man, woman, tall, short, white, black, brown, right? So it doesn't lead that person into a specific set. Now, there are other methods. There are other methods that we use to analyze the features, right? And we have the understanding of a bottom up and top down. In the bottom up processing, right? When we are doing a bottom up processing, what we are doing is that we're trying to move towards detecting that stimulus, right? Very specific stimulus. Okay? And then we're moving towards combining all of those stimuli in order to understand that stimulus as a whole. Right, we're trying to understand that stimuli as a whole. In the top-down processing, however, we already have a hypothesis of that whole, right? Have a hypothesis of that whole. But now we're moving towards the whole, right? We're moving towards the whole of that stimuli. And we're trying to check out for features, individual elements that's going to allow me to recognize, oh, this is what I was looking at. So let's look at our previous example. You'll see, okay, here's an individual element. So this looks like a beak, right? These look like feathers of a duck. So that's another individual key element of the visual stimuli. So because it has the beak and the feathers, I'm going to say, okay, it was a duck. So notice that in this case, you did top-down processing because you're formulating a hypothesis. Okay, it looks like a duck as a whole. Let me examine for specific features, i.e. the feathers, i.e. the duckbill, right? Therefore, I was correct. It had to be a duck. Whereas in the opposite sense, right, we would detect specific stimuli, right? We don't have that whole yet, right? We don't have that whole yet. So we would say, for example, I have the whole, right? I have the whole, and I say, okay, these are the specific elements that go to it, so I must be correct. Right, so notice that one goes from the whole to individual, and the other one goes from individual to a whole. Right, the idea of that whole image. All right. Now, we're looking into the picture as a whole. We like to utilize Gestalt psychology. And actually, this is utilized in some forms of therapy as well. This is used in some forms of therapy because what we're trying to do is saying the whole thing is greater than just merely saying the sum of its parts. And this may be a little difficult, right? For people in engineering, for example, because you can say, well, what do you mean? Right? This is an engine. This is a diesel engine. So the engine is an engine because of its elements, right? Because it had certain parts to it. Well, Gestalt psychology proposes that that whole engine is greater than just simply saying, well, this bolt goes here, and then this line goes to here. So Gestalt psychology would say this engine is greater than just adding its parts, right? Now, why is that relevant? Well, because just looking at a stimuli, right? For example, just looking at an image, right? Just by looking at an image, we simply don't get the whole of the image, right? So one of the things that we would need to consider is what elements go into understanding that individuality of those parts, and how do they make it greater? How is that whole greater than just the sum? Well, the first thing is the phi phenomenon, right? The phi phenomenon. This is an illusion. This is an illusion that we create by simply presenting visual stimuli in very rapid succession. What does that mean? Well, think about a flip book, right? When we have a flip book, it gives us the illusion, right? The things are moving at a very fast rate, when in reality, there is no such movement. There is no such movement, right? So we have a flip book. Notice that in that visual stimuli that we are coming across, we're coming across with that stimuli, it's greater than that sum of its parts, right? It's greater than the sum of its parts. So another aspect that we would need to consider, think about figure and ground, figure and ground. And in this specific case, in the figure and ground case, we go back to our slides. We can share our screen. You'll notice that in the figure and ground, it's a fundamental way to notice and organize our visual perception. So for instance, if I give you an example, here, I'll pull it up. So if we have a figure and ground, think about the background, right? Think about the background. So in this specific case, right, some individuals would say, well, there's two people, right? There's two people looking at each other. This is the forehead, the nose, and the lips, the chin. And some people would say, well, what I see is a figure, right? Or I see a background. So here you would say, I'm focusing more on that foreground, and you say, well, it's probably a vase, like for flowers and such, right? So that's what figure and ground is, right? We have another example here, very similar to the previous one. Do I see two human-like figures, or do I see maybe a candle holder or a vase? Because in our previous illusion, the rapid succession of images leads us to believe that there is movement. So this will be the phi phenomenon, right? There is no movement, but your brain is processing the image as such. Just like with our other aspect of having the foreground. Now, another thing that we use in order to understand proximity, to understand the whole as being greater than the sum of its parts, is proximity. We tend to think that things that are near each other must belong together. And boy, do we do that all the time. We even do that with people, don't we? If we see Peter hanging out with Jessica, that means they're together, right? So we even do it with people, right? When in reality, one doesn't pertain to the other. So in order to give you an example, let's see. In this specific case, we would say that aspects that are together must belong together. So this would be a good example. We would say that in this particular case, these dots belong together because they're close to each other. And there's no such thing. Each of these dots is individual in their own regard. But we think, oh, they must belong in this fashion. They belong together in this little square, and they belong together in this square. By the same token, right? Closure, it's another method that we can say they create a sense of a figure, right? They create a sense of a figure. So for instance, we have things that are together and we're thinking, well, they're forming a picture, right? So this one's actually a really good example. Notice that in this example here, right? In this example here, we have, they almost look like Pac-Man, don't they? But notice that in the closure of these images, notice that they're giving us the understanding like there must be a triangle here, when in reality, these are three independent moon-like structures, right? So that's another way that we use to inform our perception. In a similar sense, we tend to group things together simply because they are similar, right? Simply because they are similar. So for instance, in this illustration here that you have on your top right, we notice that these dots here are dark gray. Therefore, they must belong together because they are similar. Now we're creating the image of a number 2. Now, another thing about Gestalt psychology is that we also look into simplicity. We tend to combine elements. We tend to group elements together in order to form a picture. So for instance, in this aspect here, notice that you are grouping a rectangle with a triangle, when in reality, they're individual pictures, right? They're individual images. One of the last aspects that I like to cover is continuity. With continuity, we also have a tendency. We have a tendency to being led to a direction. So for instance, this aspect here, you'll notice that it appears like these dots are leading towards this direction. But we simply don't have any proof of it, do we? These dots are individual. They're not moving. They're not going towards the bottom right. They're actually not moving. But it's giving us that perception that, yes, they're actually moving. They're going towards the bottom right. Now, in order for us to perceive depth, to perceive distance, depth perception is simply an interpretation. It's simply an interpretation that we have in order to make an understanding and say, is this far away or is this nearby, right? We try to use cues, right? We use cues around us in order to inform our decision, right? We try to use those cues in order to inform that decision. Some of those clues can involve binocular cases, right? We can use clues about the distance based on the information that comes from both eyes. So for example, we see a little image of a person and we're going to use the information that we received from each eye in order to draw an understanding and say, okay, this is how deep, this is how far away that image is. However, we may have retinal disparity. Retinal disparity. And in regards to retinal disparity, we have different views of the same object. If you want to try that out yourself, all you have to do is close one eye, shut one eye compared to the other eye, and notice how that image is going to move slightly, which is why we will need the combination of both fields, right, for that depth perception. That is what we would call molecular depth clues, molecular depth clues. Here, what we are discovering are clues about the distance, right, for each image alone. So if you were to conduct that little experiment of shutting one eye and rapidly shutting the other, you notice that each one has an individual perception, right? And they're going to superimpose each other in order to create that distance. Now, we also have the situation and where we can have a pictorial depth clue. And now we can start seeing, for instance, an example of something that is in a flat picture. So in this case, imagine a picture where very close to it, you have a deer, right? So you have a deer that appears to be larger in that image. And then in the same image, you have an elephant. So it's really small, right? So in the same picture, you have a deer in the very front of it, because it's so big. So we try to think, okay, well, then it must be closer because it's bigger. Whereas the elephant that somebody drew that was smaller, right? We think compared to this deer and the elephant that's in the back, that's small, it means that this deer is closer because the deer was drawn, right, in a really large fashion. And an elephant that we normally associate with something really big, really small in that background. Any questions about that? All right. Now, there are some issues with our perception, of course, right? When we are talking about that perception, that is perceptual constancy. We have a tendency to think that in our experience, we have a stable perception when we're thinking about something that's continually changing. It allows us to have some sort of order in our world. We try to give it some order. These images that are constantly moving, we have the tendency of our brain has the tendency to provide some sort of explanation, right? This is where we start thinking about visual illusions. This is where this order that our brain is so desperately trying to provide to us, now our brain has the inability, right? We don't have an explanation anymore between that appearance and what reality is. Now, we're not going to cover the inner-liar illusion here today. But what it is that generally we have the ability in Western cultures to be able to perceive corners, right? Because all of our structures and all of our buildings tend to be square, tend to be rectangular, they have corners. Whereas in other areas of the world, for example, some villages, in other parts of the world, they don't build their buildings as such. They generally tend to be round, and therefore they have a really difficult perception with identifying square or angular rooms. However, this has not had good consistency, right? In the sense of data, it hasn't had a lot of consistency when we're talking about research. Are there any questions about that? Good deal. And I'll see you guys next lecture.